Hi, everyone. I'm Yue Wang, a PhD student at Rice University and working with Professor Ian Lin. I would also like to thank our collaborators from Texas A&M University. So first, the outline of today's presentation is first I will briefly talk about the background and motivation part, and then I will introduce our contributions, which include 3 different levels. And at the end, I will give a brief summary of the presentation today. So first, background and motivation. So now we know that deep learning actually is everywhere nowadays, right? So a lot of applications trying to combine themselves with deep learning together to improve their performance into a new high level. So for example, autonomous driving, AlphaGo, virtual personal assistant, and smart robots. So all of these applications are like in some way changing our daily lives. And all the applications combined with deep learning actually are powered by deep neural networks, which are called DNNs. The problem is that training such DNN models is very challenging. So here I listed some challenges. The first challenge is about the training speed. So here the results is using ResNet performed on the ImageNet dataset. And the ImageNet dataset is a popular dataset to do the classification tasks. And ResNet is also a popular neural architecture. The number after it, for example, 18, means ResNet with 18 different layers. And here we can say ResNet 18 has error rate about 10%, which means the accuracy is below 90%. So it's not acceptable one. But we can say ResNet 152, which is more complex one. It has about 94% accuracy. So the performance is actually acceptable. But we can say the training time, it costs us 1.5 weeks to train this model. So it's not acceptable, especially for some groups that they do not have that much GPU resources to train the models, right? So such a long time training brings considerable energy cost because you need to keep your machines on for a long time. And also it brings low productivity for machine learning researchers. So in a new paper, researchers performed a lifecycle assessment for training several common large DNNs. They found that the process can emit more than 500,000 pounds of carbon dioxide equivalent, which is shown here. It's more than 500,000 pounds. And it's 5 times the lifetime emissions for average American car, right? And that includes manufacturer cost of the car itself. So from the results, we can say training large DNN models are really emitting a lot of carbon dioxide to the environment, and we are actually not doing research, we are hurting our environments, okay? And also, training such neural networks on the cloud computing services will cost you millions of dollars. So we're not training, we're just firing our money. Yeah, so such a big financial burden says no to individual researchers, and also for even research groups, they cannot afford such high cost DN training. Sorry. Okay. So another challenge is about the on-device training. So the traditional way before on-device training is that we first train a DNN model on servers or computers. Then we move this trained model from computers to the edge device side. But sometimes we do need on-device training. So we need to train our models directly on the edge devices. Okay. So why do we need on-device trainings? First, we can make a model that is tailored to some users' own wishes or needs, because the users are seeing different data, seeing different scenarios. So to keep the model updated to the user, we need to keep changing the model to the latest data. And also, because training happens on device, we can overcome the privacy issue. And also, we can reduce the communication cost and latency. But the problem is, on-device training is challenging because edge devices are resource constrained because they are normally powered by batteries, and such batteries can normally drain, performing high computing intensity works like DNA training or DNA inference. And also, they are small form factors, which means they cannot offer you high computing speed. It's very challenging for DNA training, especially. So then I will introduce our proposed contributions. Before that, I will first let you know that our energy results are measured on FPGA board. It's not computed using equations. It's measured in real devices. So the reason why we measured on real devices is that energy cost actually consists of two parts. The first part is computational cost. This part is can be easily calculated because given the parameters, given the number of operations in the DNN, we can easily get the number of computational costs. But for data movement, it relates to memory hierarchy, data flow management, and so on other issues. So we cannot easily give an equation and calculate the number of data movement costs. So that's why we use FPGA to measure the energy results. And also, we connect the PC screen with the FPGA board. So PC screen serves as a terminal here. We control the FPGA board using that screen. And also, in the end, we use power meter to measure the energy cost of our model. So here is our proposed energy efficient train. It consists of different levels. So from different levels, we are trying our best to squeeze unnecessary energy costs during the training process. So first, from data level, stochastic mini-batch dropping SMD. That means during the training, we just drop the training data at 0.5 probability so that we can save the energy cost for training that part, that drop data. And the second level is model level, input-dependent selective layer update, which means we only select portion of the model to update during the training. So we don't need to update the whole model at the training process. And the third level is algorithm level, predictive sign gradient descent. So during the training, we need to calculate the gradients of the parameters to update the parameters, right? So in the traditional method, we need to calculate the full gradients of the parameters. But for our proposed sub-technique here, we just need to predict the sign of gradients. And we use the sign of the gradients to update the parameters. And it will have a much lower cost than computing the full gradients. So first, SMD, as I've mentioned here, is to drop the training data at 0.5 possibility. Although it's very straightforward, but from the experiments results, we can say it's very effective, right? So the x-axis means energy ratio. So in the same energy ratio means we use the same energy cost to train a model. And the y-axis is test accuracy. So for example, we compare these 2 points here, and our proposed technique has 0.86% higher accuracy than the traditional standard mini-batch training ones. And also for other points, our technique achieves higher accuracy consistently. So another level is model level SLU. So as I mentioned, it is only every time it only chooses part of the model to update. For example, for these 2 different images, we select different parts of the model to update. So we can easily say the first image is a little bit harder than this one. So for the harder images, it will select more layers to update because it can learn more information from such images. And for relatively easier images, it only chooses part of the model to update. Okay. So to achieve this, we propose an objective function here. We just add a new term to capture the computational cost. And it has only negligible computational overhead so that we can still save the energy during the computing. And we have gating functions here composed of recurrent neural networks. So we use LSTM to tell us, given a particular input image, which part of the model should we choose to update. So here are some results of combining SLU and SMD together, and we can say compare with this stochastic depth. So this method is also a previous one technique to achieve efficient training. All right, so it's a baseline. So comparing with this baseline, we can say our techniques combine these two sub-techniques achieves higher accuracy consistently here. Okay, the third level technique is called PSG. It's from algorithm level to trim down the energy cost. So actually this sub-technique is inspired from the sign SGD. So sign SGD is using the sign gradients to update the DNN model. So the observe, without using the full gradients, we can only use the sign of the gradients to update, and we can have a good performance on the training. To compute, to get the sign gradients, in their method, they still need to compute full precision gradients. So there is no energy saving because they first compute the full gradients and then take the sign of it. But in our proposed PSG, we don't compute the full precision gradients. We only predict the sign of gradients using low-cost bit level predictors. Here, given this, given this equation. And also, we proved that prediction failure probability of PSG is unbounded by a small number because we are predicting. So there is a failure probability we can have for the prediction. And we proved that the failure probability is bounded by this number, which is a very small number. And if you want to know more detailed things, you can check our NeurIPS paper this year. And here is the performance of combining three techniques together. And we can say we use two different data sets on the ResNet architecture. And for this combination, we can easily achieve above 80% of energy saving while we have only very small accuracy drop here. So to summarize today's presentation, first I listed some challenging points of DNN training from three perspectives. First, training time and carbon footprint and on-device training. And then I introduced proposed method energy efficient training from three different levels to trim down the energy cost of the training process, which are data level and model level and algorithm level. Then I show a promising performance of all the techniques. Yeah, that's pretty all my presentation today. Any questions? Yeah.
Measure the cost of data movement versus computational in your final results that you showed?
We are. So your question is, can we measure the data movement cost using equations or simulators or real devices? Yeah, we can measure the. Yeah, we can measure it because we are using this power meter to measure the real energy cost during the running.
But you can't separate it out, is that correct? You can't say so much was saved due to less data movement?
Yeah, so we got the energy saving because we first run the baselines methods, and then we run our methods. So we just have two numbers. We do some calculations. We have the energy savings. Yeah. Another question?
I see you use the, I see in the model level, you use the LSTM to pick which image you select which layer to train. Can you give me a little?
You mean SLU?
Yeah,
Okay.
yeah, the last point. Yeah.
So here?
Yeah, the last one you decide to use the one. So for different like these two images, the upper one is more difficult and the lower one is more easier, right?
Yeah.
So you predefine the upper one is more difficult?
No, actually, we're not defining it. So it's observations. It's not definition. So during the experiments, we observed that simpler images tends to have such decisions, tends to update less layers than some complex images.
Oh, okay. So it's models, you behave that way. You are dealing, if I think you predefine
Yeah, so the gating functions learn that way. They can learn for such images, it will update more, and for such simpler images, it can update less. At the same time, it can achieve similar performance. Okay.
Yeah, let's fan our speaker again.
Okay, thank you.